Now we want to find an estimate or to prove an estimate for the Fourier-Haar coefficient for the case when f is from Lp. So, theorem, second or B, f is from Lp, 0, 1, then where this omega p 1 over n f is the modulus of continuity, and it is determined p modulus of continuity, and it is determined by the formula I'm going to have here. So delta f supremum 0 less than h less than or equal to delta and the whole thing raised to 1 over 3. We are going to use this expression for the modulus of continuity. Now let's prove the theorem. Absolute value of C and F, as we already saw when proving the first part of this theorem, is less than or equal to 2 raised to power k over 2 times integral from I minus 1 over 2 to k to 2i minus 1 over 2 to k plus 1. So this is the left half of the dyadic interval. And here this difference in absolute value. Now we will use Holder's inequality after this point. Less than or equal to 2 over 2 raised to power k over 2 integral with the same bounds, 1 raised to power q raised to 1 over q times this second factor here. Now the coefficient, of course we have 1 over p plus 1 over q is 1. Now we will have 2 to k over 2, and then the length of the interval of integration is 1 over 2 to k plus 1, and it is raised to power 1 over q, and 1 over q is 1 minus 1 over p. So I can write here 2 to k plus 1 raised to 1 over p minus 1. Then, because the smallest value which this lower bound for the integral takes is 0, and the largest value for the upper bound of the integral is 1 minus 1 over 2 to k plus 1. Recall that n is 2k plus I, where I changes from 1 to k. So we use it here. The largest value for the upper bound of the integral is 1 minus 1 over 2 to k plus 1. Therefore, we can use this estimation with the help of this omega p and get omega p 1 over 2 to k plus 1 f here. Now let's simplify a bit this factor. We don't need the formulation anymore, in fact. and then equals, this equals 2, 2, so will be k times 1 over p minus 1 plus k over 2, that is 2 raised to k times 1 over p minus 1 over 2, and then 2 raised to 1 over p minus 1, and then omega p. In fact, let's have immediately n here, and we notice that because 1 over 2 to k plus 1 is less than or equal to 1 over n, because this expression for n, we have this estimate for the modulus of continuity as well. The modulus of continuity at this smaller delta, 1 over 2 to k plus 1, is less than or equal to modulus to p modulus of continuity at 1 over n. So this is expressed here. That fact is expressed here. Now this will be denoted by star. Now after this step we discuss cases. If p equals 2, it's easy to check, everything holds, the theorem holds. But when p is less than or equal to 2, we notice that 1 over p minus 1 over 2 is positive, and therefore this 2k is, because 2 to k is smaller than n, we can put n in the place of 2 to k and get something larger. So it is justified to have here star is less than or equal to n raised to 1 over p minus 1 over 2. And we also notice that 1 over p minus 1 is always non-positive, because p is greater than or equal to 1. Therefore, 2 to 1 over p minus 1 is less than or equal to 1. Then we are left with omega p 1 over n f. If you remember, this was exactly the thing we wanted to prove. Now, for the second case, p greater than 2, star, we first noticed that this 1 over p minus 1, no matter what is p, is less than 2 raised to 1 over p minus 1 over 2. Let's have that fact here. So here, and then this means we have 2k plus 1 raised to 1 over p minus 1 over 2, and then omega p. And now what we need to see is that p is greater than 2, therefore 1 over p minus 1 over 2 is negative. Therefore, if we substitute 2 to k plus 1 with something smaller, in particular, namely we substitute it by n, we get something larger. So therefore, we can have less than or equal to n raised to 1 over p minus 1 over 2 omega p 1 over n f. What we get is whatever we wanted to prove. So this, in this case, theorem holds as well.